So this function can be very different. In logistic regression, this function is quite simple. Sorry, it was the wire. Logistic regression. And what logistic regression does, it's like just two steps. First step is finding the sum, and second step is taking sigmoid function from the result. And you can now open the document I've shared with you. The very first link I have shared with you. And you will see that this part can be represented like this. And sigmoid function is something like the details of this thing you shouldn't know. Just ignore. The only thing you should know about this function is how it looks visually. And this is the thing like this. This is the 1, this is the 0, this is 0.5. So for values under the 0, we have almost 0 all the time. For values much higher than 0, we have almost 1 all the time. For values that are close to 0, we have something close, something in between from 0.5 to 1, or from 0 to 0.5. And our decision about whether it is object or not object will be based on comparing with 0.5. All the formula for this F, it looks like where X and this omega, they actually vectors. One vector times another vector plus this bias we discussed before, and then get the prediction. In machine learning, this hat notation usually means that this is a predicted value. So this is logistic regression. In fact, think of this X. Long vector here. Currently 64. These omegas, it is also corresponding vector that's supposed to be like a coefficient for each X here. It means that if we want to have logistic regression for just 3 values, we will have something like this. Access is a thing that we get from data, but this wise, not wise, omegas, is something that initially is unknown. And the reason why we call this machine learning, that we show many examples to our algorithm and try to find such values for this omegas just to make this function work well for examples we show. So generally, we just use an iteration-based process and a special optimization procedure, for example, called gradient descent. It's let me to find proper values of this omegas. When we have these omegas computed already, let's suppose we already had a possibility to show to our algorithm 1,000 of examples of zeros and ones, handwritten zeros and ones. And all the time we tried show these examples to our function. We tried to find better values for y, b, and altogether this is just a set of values that we can save somewhere. And this set of values that we find during the training process is actually the model. If we have formula, if we have values for coefficients here, we can anytime take new values of x, which we get from image, and make a decision whether it is 0 or 1. So y can be something in between from 0 to 1, not including, and if it is more than 0. Larger than 0.5, we think that this is 1. If it is smaller or equal, we think that this is 0. So generally, this is a logistic regression. But the thing is that this is also the thing that we call neuron, and there's no difference. In fact, during like throughout the history of development of this math, initially people invented logistic regression, and they decided, okay, it's very weak algorithm, predictive algorithm, right? It cannot do anything about really complex things. It cannot, help us in, let's say, with understanding whether this screenshot, okay, X-ray shot of COVID-19 person or not. So too complex data inside, and cannot be the knowledge, the difference between this sick or not sick person cannot be stored in just so simple set of coefficients. Even if we have lots of them, it is still impossible to store everything all together. Yeah, and when people decided to, what if we take this logistic regression as a simple part of more complex thing and took many logistic regressions like this. We take several independent logistic regressions and put them in certain type of hierarchy or maybe web or network and create more complex construction from that. So that we have many inputs here for each logistic regression, many logistic regressions that join together in the network. And in fact, this is already and this is already neural network. Any questions about this?
No.
So when you hear about neural networks for any type of tests, inside it is based on ideas like this. Neurons can, in modern neural networks, they can be different. It's not only logistic regression. It's not only sigmoid activation function. So here we have many options what to put. It could be sigmoid. It could be ReLU. I will share a special document with you about that after we complete. But generally, the things stays the same like for all for feed neural networks. There is a question, general big question, how to find all these coefficients even for one logistic regression. But if we have a big hierarchy of these logistic regressions, what we should do when we show training examples, how we should update these coefficients. And this points us to reading like about gradient descent, and also another term that is important for neural networks. We won't be learning it in this thing in real details because it is like the thing that can be learned like very quickly. But two terms about that, I will put them in our document, and also some examples. I think it's enough for you to take a look into explanations of that and understand in brief how this couple of things work. What is important about backpropagation and gradient descent is that for each value of coefficients we are looking, we need to make really big number of computations. We need to multiply many vectors to many vectors. It's like operations we call linear algebra operations. Yeah, it is everything Um, This topic studies how we deal with vectors, matrices, and tensors, and how we multiply them, how we do basic arithmetic things on um, vectors, matrices, and tensors. Also, what is important to know here to understand backpropagation is a topic called derivatives. This is not the last situation we discussed this. I will share a special document that explains this in details. But I think I'm really sure that we don't need to spend time on learning real details how these derivatives and many multiplications are used for finding proper values of these omega and v values. But what you should understand, we in this situation, we face with lots of computations like this matrix times this matrix times this matrix. And it happens millions and millions. And for that specific type of computational task, central processor in our PC isn't the best thing, because for example, can you imagine we have here we have 8 by 8 pixels picture, right? But generally we face usually with 2 megapixel 4K pictures and quite large pictures, right? Each pixel is value, even 3 values if we have colorful image, and the size of this matrix and this vector will be very big. And central processor can handle computations on these matrices, but by splitting this computation in many small pieces and going through all the long row of small multiplications, but then like adding them together, and this is long iterational process for a central computation module. But in the market, also we have big gaming industry and big industry that works with visual data, and in order to render pictures quickly, our industry provides us with these GPU modules. We call these graphic cards, NVIDIA or AMD. They provide many solutions like that. So NVIDIA engineers, they found that it is possible to use these devices for performing this type of computations much more quickly than on the central processing, because in fact when for gaming we render the picture, we already do the same thing. Graphic card consider full screen image of our game to be a matrix that should be transformed in some way by multiplying this matrix by this matrix. And so this is the same set linear algebra operations, that we need for our optimization task. And NVIDIA provided us with special solution that allows us to utilize power of GPU. We discussed that already. What is GPU, right? GPU, graphic processing unit. If we have the one in our system, we can like send the task that implies many matrices multiplications to this GPU module. It performs computation much more quickly than central processor can do, and returns the result to our program. And when you switch your IPython notebook in Google Colab platform to use GPU runtime, it means that for computation, it will be used not only in CPU, but also some parts of computations will be performed on GPU, and so that we can get our result much faster. It can be 30 or 50 times faster. To compare, you can understand that the thing that we compute in 1 hour on GPU, potentially we compute on CPU in 30 or 40 hours. If we talk about 1 day of neural network training, and very often it happens so to be 1 or 3 days on GPU. On CPU, it would let us for maybe a half of year of training or something, because having 90 days or 200 days instead of like 3 days or 10 days on GPU means that for business it is very important to do things much faster. So GPUs are very nice about this, and it is very common case. Library that allows us to use GPU for computations called CUDA, C-U-D-A. And this is what all the data scientists need now. So if you build a research and development team for any AI project, including machine learning, it's like 95% probability that you will need one of or maybe even many GPUs for research and some GPUs for production. For example, my team uses like graphic cards this type, but this is not the only available option. Titanix, Tesla, maybe many of them. This is like a very powerful one. This is a little bit less powerful, but they are nice. Actually, almost all modern NVIDIA graphic cards support this CUDA, but they have different size of memory and different computational speed. So yeah. Just a moment. So neural network. About computations. At this level, do you have any questions, or I can remove this from board?
And on this top left corner, Graisko, what does it mean? No, upper Graiska.
Grayscale.
Yes, this is.
It means that each pixel.
Grayscale. Okay. Thank you.
So we have a neural network, and we understand that we can take a big X vector, feed each value to all the neurons, and finally get some prediction here. And to be able to do this, we need to train this neural network before using backpropagation technique. Details on backpropagation you will see in document. It took for me like maybe 6 hours to understand how it works when I studied the technique, and also maybe 1 day to implement this properly. So I spent a couple of days on learning how backpropagation works. I was like a person who worked a lot with other machine learning algorithms before that. So for some of you, it can potentially take longer. I don't think that we need to concentrate on details in this, but it is possible to understand this backpropagation thing if you want. And there are a lot of materials. Instead of digging in depth about this thing, we will try to understand what research and model development process looks like in a real project. And for now, we had a chance to see just this type of neural network. It is called perceptron, but there are alternative names for this type of neural network, and it is also this is like set of synonyms, all the same. Sometimes we call entire neural network to be perceptron, or fully connected neural network, or dense neural network. Sometimes we mention one of the layers in neural network to be dense, fully connected, perceptron, or something. We also will need to learn additional types of layers and additional ideas to handle computer vision projects and problems. Yeah, and we will also learn this type of neural network. C is convolution. Convolutional neural network, convolutional layer, and the next step we will try to understand is this time convolution. Like before we continue, I just want to mention that these convolutions, you can see how they work in Photoshop or GIMP filters. You can apply different filters to your photos by describing these filters as a small matrices. People who work with design, they know this thing already. They don't try to understand deep math about that, but they use different patterns of convolutions to filter out things from image. So you can think of convolutions like about special filters that are applied to images. And currently we have 15 minutes to 1, so let's have this as a break. So guys, I'm starting to talk about this thing called convolutional neural networks. And it is important to go through before I will be showing first example and first cycle of data science project, how it can be done in matter of research and continuous improvement of the model. And I think that basics I can explain like maybe in 1 hour or something like this. Then I guess we will need some break for lunch because it's whole day work, and after the lunch we will be switching to example itself. Is it correct, plan? I think about, let's say, 2:15, 2 p.m. 15 minutes. We can like start 1 hour break, right?
Sounds good.
Okay.
So what I'm going to talk about, it is still, again, not math, but very close to math in convolutions. And what I'm going to do is just to show the idea of what is convolution. As we discussed before, we can use fully connected neural network with any size of input vector to predict something. We can take any type of input, whether it is image or maybe some parameters of coin that we can measure, or maybe a sound or textual information, and make some prediction for the output. And for each type of input data, we know something about nature of this data and can handle them differently. For images, somewhere in the mid of 90s, Professor Jan LeCun he invents the thing called convolution that helped to reach a breakthrough in the quality of image classification. We already discussed that we can just use pixel coordinates and values for these pixel coordinates to make some conclusion whether it is cat or not. But for example, several cases that for sure cannot be easily handled by simple perceptron or fully connected neural network. Just a couple of examples. If we have an image like this and we want to tell whether we have cat on this picture or not, it is possible that we will have some images with dogs or whales or people there. For all these pictures, we should tell no cats on the picture if no cats on the picture. So very specific and complex high level of abstraction features can tell us whether the cat present on picture or not. And for human beings, let's suppose you see the picture of a girl who carries the rabbit, for example. Rabbit, very cat-like creature, right? In many situations, we can even misunderstand whether it is cat or rabbit. But you can see one small detail, maybe a piece of rabbit ear or an eye or nose that for a human being is enough to tell for 100% sure this is a rabbit. Once even one eye appear on the photo, you already know, well, is it cat or not. There is no possibility, like what we analyzed, we took pixel and using the value of this pixel together with other values, like combined decision, we decided whether it is 0 or 1, because for once we can even build some kind of probability map and decide if our pixels dance here in some region like that, this is, might be 1. If the map of probabilities like this, maybe it is still possible that we have some pixel here or here, but it is something like this, and we guess that this is 0. But this type of feature, like mapping to some probability heat map on this image, it's not a very informative feature, and is for sure not as complex as an ability to distinguish cat's ear from rabbit one, right? Because there is no such a place where we expect exact this type of pixel on the photo for rabbit or so. So we need to be able to feed to neural network some additional information to make this classification properly. We can, in addition to using like just a pixel map, potentially we could hire an engineer who will also develop special feature, and this is called feature engineering. For example, We can ask some programmer to find, to come up with algorithm that will find all the arcs like this, some applying some just computer science based handwritten algorithm. Arcs like this, and vertical lines like this. If is it possible to describe some logic that will find something like this? Just using some heuristics, some rules, like if pixel goes in this like order, maybe this is the arc, and so technically, we, in addition to this map, we can also add the feature that there is this arc, and this thing, and moreover, they go together in special order on the image in a way that potentially could tell us that this is an eye, right? Maybe also something like this, right? Additional features. So what if our x vector from this picture would be like, on one hand, the same sequence of pixels we used before, but also we can add specific type of features like values of this vector, add some additional cells into this vector, making the vector longer, and put here not only values about pixel things, but also information about, do we have this type of arcs? Do we have this type of arcs? We have this type of things. And maybe additional one, do we have them go together or something, right? So if we have additional features that already obtained from the image, classification becomes more easy. Is it clear why? So before sending this to an neural network, we also make some pre-processing to this image to dig out values additional features that we think can be very informative. It's just, but my guess, what exact features. But the thing is, even for professional computer vision engineer, it is still the set of guess. So this person would take a look at data, will understand what small features can be informative, write special functions that will find maybe things like this. Small angles, a couple of lines with angle like this. It is possible to write some logic that using many ifs in Python code will show if we have such an angle on our picture, we can make a conclusion that this feature present here and put it. And then when we feed this to neural network have additional layer of information about image to make conclusion on. But automatically, our perceptron cannot do this. We need this feature extractor. To be honest, this feature extraction thing, the thing is a layer which was the most important part of data scientist work throughout last 30 years. 80s, 90s, 10s, 20s, all everything data engineers were doing, primarily 85% was related to that. So the only real thing data scientists could use for this, write many feature extractors. In fact, filters that take picture and apply some rules to make decisions on small things here. And then they could use not only neural network, but even logistic regression. If we have many features like this, or maybe altogether, this, we many feature extractors. In this situation, we would be able to make a conclusion whether it is cat's eye or not, just by using primitive logistic regression or some other simple machine learning algorithm. But the problem is that the work that implies development of these features is like most time consuming, complex. Sometimes the quality of the feature extraction isn't nice, and to be able to create this, engineer should understand the nature of data very well. So to be able to find something like this eye and concentrate on the on this eye as a feature containing thing, we should already have this expertise from our personal life, that we can guess that cat's eye a good feature to use. But we think about cats a lot, but many things in our reality based on data that we know very few facts about this data. So we cannot easily intuitively see features which can be descriptive or not. And for that situation, maybe it is a nice idea to make system learn these informative features automatically in some way. This is one thing. Another thing, what if our eye much smaller or much bigger? Another problem, we need to be able to understand that we have this feature for any scale of the object. And convolution is the thing that allows us to solve both and some other problems about that. So the idea of convolutions initially was like scaling problem, solving scaling problem. If we have I like this and I like this, we potentially could come up with some algorithm that help us like add additional transformation to the picture just to see scale independent features. And The simple convolution that we can do is, what if we use for scale and things like that? We take small part of our picture. The simplest way to reduce resolution is to take this pattern, take all these four values, find an average one, for example, or maybe the largest one. Let's start from average and generate new picture that consists of this result and the size like this. So we reduce the picture size 4 times, right? And if we had here big object, here it becomes 4 times smaller. And we can design some feature extractor that is able to extract object of this size by maybe again by programming by hands, hard coding this type of features. But if we have an image and goes through this type of convolution many times, here we have one, here we so on. So each time we check for this feature. If any output of this feature gives us positive result, we know that we have this feature in some scale on the photo. So this is already convolution. Convolution is making something smaller by reducing its size. This type of convolution called pooling, and we have many types of let me check how it should be written. Yeah, double L here. It's like pool. No. But this is not the only way we can do. We can take not average, but max value, so that we take the brightest one pixel. Or we can take alternative size of this convolution window. And each time we come up with new way to extract value for new pixel, we come up with different way how we which window, convolution window we select and use. For example, the simplest one, we just put here coefficients 1, 1, 1, 1, 1, and we compute the value of this pixel like 1 times the value of this pixel plus 1 times the value of this pixel, so that we can get something like and finally get the result, let's say, so this is the value of this pixel. But this coefficient can be different. Some of them can be zeros. And sometimes we can apply not multiplication here, but instead we can use max or mean value. So we get all these pixels, find the minimum value, and return it as a value for the pixel, so that we can get max and this is the simple way how we can use convolutions. Just reduce the size of image using special rule. But in addition to that, we can have many more types of convolution.
But to which extent we do this size reduction until we see that algorithm works correctly? Yeah?
Usually we have
model. No, I mean,
yeah. Usually we design. We guess that this number of convolution steps and types what we want to use. We check. We build such a system, train it, and check hypothesis how it works well or not by evaluating the result, how well it predicts. We can change different architectures of neural network and finally understand which works better by applying evaluation. But the thing is that we also need to talk about another type of convolution.
And the purpose of doing this is to save computing power or increase.
Not only that, also like to make it possible, first of all, to ignore the scale of the object on the image, because we reduce the size of image and all the time check for pattern of this size. Reduce, check, reduce, check. We all the time check for one simple thing. And during this, let's say, sequence of convolutions, at certain point, we probably will have this object of a size that we are able to handle. But this is just one type of convolution. We also, this way, can extract some more information if we use a little bit more complex convolution.
And are you saying devolution, evolution? Could you write the word? I'm not quite sure what the word is.
It is in the document already.
Oh,
it is convolution.
Convolution, thank you. I see it now.
Mm-hmm. Please don't hesitate to Google the word, because you'll see it like in output, in Google output, like maybe first 3 or 4 links. So let's suppose we have an image like this. I understand. I need darker thing. And we have just one black circle here. We want to be able to find something informative about this thing. And we can try many different convolutions on this picture. So let's suppose we have pixels like this, and this is already the thing I have. Sorry, it is almost not a circle with such a small resolution, but generally it is a circle, right? So, and we apply some convolution we take this convolution, this size of window, and the description of this convolution could be like, convolution actually is a formula that can be graphically represented like this. And we put like numbers here like this, 0, 0, 0, 1, 1, 1. And for this situation, we have 0, 0, 0, and here we have 255 values, 255. So the output value for this pixel will be something that means like -1 times 0 plus 0 times 255 plus 1 times 255, taking all the pixels here, like 9 items in this sequence, and get the result value for some pixel in the future. But what we can do about this is not like moving the window like this to this position. Instead, we can use shift just by 1 pixel. All the time by 1 pixel, then we can reach the end of the picture and move 1 pixel down and continue this. So that we can apply this convolution to picture like this. Let's suppose we have picture of this size. And we decide to use convolution window like this. And also we decide that our step will be 1 pixel. So this is the first time we take convolution. This is the second time we take convolution. Third time. Fifth time.
One more.
I'm just trying not to put mistake here and here. So we have several convolutions in this row, right?
Yes.
And each convolution potentially produces a new pixel value, right? So the answer, here we have 1, 2, 3, 4, 5, 6, 7, 8. 8 pixels on initial image. And we have convolutional window 3 by 3. How many pixels we will get in final image in this row? Could you please try to calculate?
6.
Why?
8.
So we have 1, 2, 3, 4, 5, 6, 7, 8. Do you think we will have 8 pixels as output?
No, 6.
It's correct, but why? And I want others to understand why 6. Let's suppose this number would be like 30, initial number. What it would be finally? How many?
28.
Okay, correct. So currently we see the formula that if we have n by n resolution of this picture, and we use this type of convolution with this step, what we have as an output is n-2 and n-2 resolution, right? This makes our picture to be reduced much slower, step by step. This is one thing. But also we can apply much more complex coefficients here. Moreover, like to avoid this actual size reduction, usually before applying such a convolution, we add special margin here. So we initially add 2 pixels for each axis, just in order to preserve the picture size. The only thing, the image slightly reduced in its size. It's just for convenience, because it is easy, much more easy to write the code that handles all the time the same type of convolution. So if we add like special margin in computer vision, we call it padding. It's for reason, you understand, like just padding.
You have to add padding for every step?
Yeah, you add padding, then make convolution, and you get the image of the same size. So the size of parameter for all upcoming functions will be the same. So that your convolution doesn't reduce the picture size. In fact, it just reduces the size of objects on this picture. And also, there is a very important property for this convolution. If it is more complex than just max pooling or something like this, maybe it is 3 by 3 with some coefficients selected in a sophisticated way, in smart way, we can find such types of convolutions that allows us, for example, to filter out all the vertical edges from the image, or horizontal, or maybe find just edges for the entire picture, so that we can take a picture of anything, run this convolution filter on top of the image, and get, let's say, pencil sketch of the picture. You can try this in Photoshop. It is really available. Let me check. Maybe I can show this easily for you. Just a moment. I'm trying to find corresponding filter for you. Just to you can do this pre-processing your by your hands. It's okay. Great. So I'm sharing the screen for you, just to show how convolution can work. Do you see the screen?
Yes.
I took just a random picture using the Linux software called GIMP, General Image Processing Program, and I want to use this generic convolution matrix filter. See, it's actually a matrix with some values for each convolution cell. It is 5 by 5. Technically, we can come up with any size here. So let's try using the default one. Nothing serious happened because it is too large for that. Let's try. Maybe we can come up with an alternative image. Will be much more informative. Let's use okay, I want to have such a picture and apply convolutional filter for the. So we can use something like similar to what we have on the blackboard, actual whiteboard. Let's try something like this. Okay, sorry. And we'll see what we get. I'm just guessing. I have no real knowledge about what we will get as the result, but let's try. See? Application of this filter to big black spot made us see some.
The right-hand edge.
Yeah, something like this. And depending on what type, what size of convolution, what coefficients we have, we can detect many different things. For example, we can really come up with such a convolutional filter that will create like pencil-like style sketch of initial picture, or many others. And these convolutions, if we put them together in pipeline, we can use these convolutions to extract very complex features like this. So if we have many convolutions in line, in fact, we can extract this cat eye or something automatically. But we still need to predefine coefficients for each convolution and know its size. Even if so, we can utilize convolutional neural networks for getting a lot of interesting information from there. But it is also possible to make system learn these coefficients automatically we can just define the size of convolution window and make the system learn how exactly we are going to filter these images. And system in using iterations will be coming up with such values for each cell of each convolutional window that finally we'll get more descriptive high level features that better characterize cats, for example. So if we also train the values for these convolutional windows for our domain, we can get better classifier of cats and dogs, for example, just using automatic procedure. And this, when people came out with that, it was like 2010 or something like this. It was a real breakthrough. Starting from 2012, maybe, all the competitions about computer vision were like one just with convolutional neural networks. Everything that people used maybe for 4 or 5 years were just simple convolutional neural networks with some more sophisticated convolutions, better pipeline of this convolutions. They just were able to find more suitable convolution sequence for this type of pictures, and one competitions. I mean competitions like classification, image classification competitions. There are like several very well-known competitions in the world established by IBM, Microsoft, and some Kaggle for sure, that primarily the result of this competition changed which model is currently the state-of-the-art model. Each year we have breakthroughs there, some new convolutional architectures. I'd say that modern, very powerful neural networks, they contain not only convolutions combined with fully connected layers. They have very complex pipeline, many different tricks inside, but generally the main block we build these neural networks from is convolutional block or fully connected block, and that's it. All other things is like smaller details, like maybe some additional types of layers, but this is a general thing. So currently you should understand what this convolution is. And before we continue, I want you to ask questions about that.
Could you please tell what does it mean -1, 0, 1? So how it influences the behavior?
This one, right?
Yes, yes.
You understand that we have this convolutional window and apply it to a picture, right?
Yes, yes, yes.
Here in the picture, we have like values for pixels, right? Here it may be 0, here 12, 114, 1, 13, 19, 191, and 255, like this, right? We take this convolutional window and apply it to this part of the image. In a way, like this is a coefficient, this is a value, and we time this to this, respectively. and get this. Let's go through it and compute. It's like -1 times 0.
Okay.
So we get long sequence of values, and finally we can compute the value for new pixel that we get on,
Okay.
on a new page. Actually, what I recommend to you is to experiment with convolutions in Jupyter Notebook. It's not mandatory thing, but it is something that you can easily done. We tried this GIMP software to apply convolution, but you can use Python code to apply any convolutional window. It's if you have time for that, you can experiment with this. You can develop from scratch some filters you want to experiment with. Yeah. About these pairings, currently we know that we have size of convolutional window 3 by 3 and step just 1 pixel. What if we have a step equal to 2 pixels? Or what if we had 4 by 5 convolutional window? Different parameters of convolutional window and steps implies different values for this padding. Is it clear? Okay.
But how actually? I think it's not. Let's say how you know which convolution matrix you shall apply. It just you play it and it's something by accident you get a good result, or there is some approaches that you know that okay, if you apply this you will get this output. So
yeah, good question. So I already tried to touch this topic, but let's discuss this in detail. First of all, when you're an engineer in this field, you have already developed some intuition what type of convolutions allow you to obtain what result. But this is still not enough to have some intuition. Instead of that, teams, they built research pipeline, not only about convolutions, but about overall architecture of neural network. How many convolutions of what type, how many fully connected layers we have, and how they connected with each other. And let's say we came up with this, and 100 different architectures that are quite similar, but have some differences, right? And we can run a technique called grid search. To be honest, the most primitive technique. When we check all the architectures we came up, we train all of these networks and see what the final level of accuracy of classification we got. The architecture that shows better result further considered to be the best one. So this is the answer. The most primitive way is like this. I need to mention here that grid search, it is clear that this is very, very computationally expensive thing. And if we can avoid stupid grid search, it is a nice idea to do that, because spending hours and weeks on retraining many architectures that don't produce a nice result, and just one of them will be a little bit better. It's like not very smart, but sometimes this is the only option we can do. Of course, modern machine learning science allows us to use some mathematical background techniques to reduce the size of space which we are testing for the best option. And this way we like reduce the size of grid search space, or even completely remove it. But sometimes it is still a nice thing to do, to use grid search. Later, we will see many already existing architectures for different computer vision tasks. And yeah, before we continue, so we have before our break, we have like 15 minutes, right? Let me also pay attention to what type of tasks in computer vision we can solve. We have a picture of a bird. And we want to be able to train our system to tell us whether we have a bird there or not. So we need to classify images using this type of pattern. Like if we have a bird can appear in a very wide range of different appearance. So it could be like this also. So it's a little bit inconvenient to draw like this, but it is still bird, right? So this is bird, this is bird. We also have other pictures in our training set, for example, mushrooms and maybe cats. And so on. So we have positive examples and negative examples. This is just a classification task. But what if we need something more? Not only classification. But also maybe ability to find where exactly in the picture we have this object, locate. In addition to having the answer about class, we also want to know coordinates. So maybe we also need something it's an official term, so that I write it like this. Region proposal neural network that guesses where the object located on the picture. What if we have many birds here, one like this and one like this, flying somewhere in the sky? So that we also need to be able to do this with multi objects detection. So classification, origin, proposal, together they give us a chance to solve the problem called object detection. And you have already seen this on the video I've shared with you. When people walk, they have bounding boxes. So we classify this image to have some people there and find regions where these people located on the image. But also probably sometimes we want to be able to have like Google Pixel does and some other applications. When we take a portrait photo, a person here, right? We have this photo. We want to be able to understand that this is some shape on the photo that is actually a person, but all other stuff split by this curve is a landscape. And if we can separate the person from landscape, we can apply different filters on in our editor. For example, we can add Gaussian transform to this to make it like more bluer. Maybe we can remove the color. For example, like let me check. I will try to find the image. Currently, you can see the photo, right?
Yep.
The lady is still colorful, but all the landscape is grayscale. What happened here is computer vision algorithm was able to find this bounding curve and split image in two different layers. To one layer, it applied like black and white filter. Girl wasn't changed. And then we got such an image. This task is called like image segmentation. Also, we can discuss face detection, face recognition, and many others. Like let's say there is a list of common computer vision problems that very often used in business, and this list maybe of size like 50 or 100 different tests, but more common ones maybe like 10 or 12. So yeah. In many solutions, we just need to catch the pace and maybe detect the mood, or detect the gender, or detect the age, or even race or something.
What are the commercial reasons to be catching mood? What things are people doing with that?
Actually, it's weird, but many businesses are asking for this feature. Sometimes it's not easy to deliver because of some conditions of taking these photos. But for example, 1 year ago, we had a request from network of haircut services from Norway. They wanted to be able to detect a human mood after having a haircut, just to collect statistics. To have some kind of statistics for further analysis, which master is better, who was disappointed, and like maybe try to reach this person and ask what's wrong or something like this. So mood isn't easily detected, but it is possible. Not only mood.
Do you know what they did with that data?
Actually, yes. The thing is, according to GDPR, it is impossible to store photos like this in Europe. But if algorithm analyzes the photo and doesn't save it for future usage, it is legal. If question about that. Yeah, of course, especially in Europe and San Francisco and California in general, there are too many regulations, legal regulations about capturing people. It's very complex now. To be honest, for Western world, it's a big problem because this is one of the reasons why China wins AI war. Because in China, you can do with data anything you want if you go together with like their law. If you share your result with their intelligence service, you can do anything. So
Wow.
you can collect data, you can capture people, you can store them, you can use this data for further training, you can violate any personal rights, just share this with government and it's okay. This is not the case for US and for Europe, and this reduces possibilities to like experiment with data and utilize the power of data.
Yeah, that's crazy.
And what's the difference between image segmentation and image allocation proposal?
It's important, yes. Object detection means just finding bounding box. Bounding box is like this coordinate and this coordinate. And we know the rectangle that includes the object. But for image segmentation, it means that we need to find the curve.
Okay, okay. So it's more complicated. It's more more consumption,
Yeah.
power consumption. Yeah.
Yeah. In fact, when we do this, let me show you. Like, let me show an example of that. Actually, it's again the task of dealing with buildings. I just want to. I'm going to open my business chat now to show you some screenshots there. Please don't be surprised too much. Actually, let's go through this chat together. It's not nothing that can. Weird thing. Oh, actually, it's interesting photo, and it's from real prod. Do you see that?
Yes.
So here you can see, on one hand, you see some bounding boxes here, but also you can see roof parts segments. This is called instance segmentation. There is also another task. It is called like semantic segmentation. And the difference is that for semantic segmentation, we would be able to find just a footprint of the house. It would be of the same color. But if we have instance segmentation, we can find each part independently and consider it to be different objects. So we need to know that this triangle is an object, this polygon is an object, and so on. So in fact, we have many objects for that form together the roof of a building, and this way we can analyze it in more detail, maybe more accurately. Actually, also you see here captions like roof and 1.000. This is the confidence with which system thinks that this is the roof. For example,
is that perfect confidence?
Sorry?
Is one perfect confidence?
Yeah, it's like 100% sure. Actually, it looks like nice, but here it isn't nice. When a system is too sure about something, it means that generally this system has a weakness in manner of generalization of its capabilities for general case. It means that it is also about like people. If a person is sure 100% about something, it's weird because human beings cannot be sure for 100%. You should always put some doubts in about your opinion, because this is the only way how you can correct your understanding about the world if you get new data. And for machine learning system, this is the same. If it is too sure about something, nothing can change the opinion. So it would be better if this confidence would be like maybe 89, 93%. It's nice, but not 100%. So currently, I think we reached the point when we have to create, let's say, 90 minutes break. So, or not 90, like, let's have a break till 15:50, like 10 minutes before we will continue. Okay. So you can see GitHub page about convolutional neural networks, but also this document covers some elements of pipeline, how research is usually done. I will be explaining it. Sometimes I will switch to GitHub page, but also I opened the document through Google Colab to make it possible to run in place. Do you see my screen?
Yep.
Right. Okay, we just discussed what is convolution about neural network graph. Generally, we discussed before that we understand a neural network as a sequence of layers. In each layer, we can have many neurons that in fact connected to something like this. This is fully connected neural network. We call this perceptron. FT or dense. This is the same. But also, we discussed that there is such a thing as convolution. So potentially we can also have some CNN layers here. There is the input. So it's just an example of some neural network that consists of a couple of convolutional neural networks, two fully connected neural networks, output layer that in fact is just a logistic regression, as you remember. Here, I want to mention some specific things about what you can see with neural network graphs. And one important thing that, first of all, you can mix different layers together in one neural network architecture. Here we can see convolutional layers, fully connected layers, actually output layer, despite being represented like one element, one neuron, it is still a fully connected layer just the size of 1. And for each layer, there are many specific meta parameters we can set up for them, at least a neuron count and activation function. As you remember here, sorry, here at every output of neural network, we can sigmoid or some other activation function. For example, ReLU. It is still possible that we can see there is something different from that, but sigmoid, ReLU, and linear are like the most common. There are different reasons why we put different activation functions at output. One of the reasons why we can select ReLU instead of sigmoid is complexity of training the neural network if internal layers created by sigmoid. Yeah, ReLU is a little bit less complex mathematical function, and it means that we can use it in the same way as sigmoid, but a neural network will be trained much faster.
Do you mean less complex in terms of computational power?
Yes, exactly. Good question. I even can explain. As you can remember, we have sigmoid like this. ReLU is a function that looks like this. Oh, sorry. This is ReLU. So we have a special point here. Before 0, it equals 0. After, it's like linear function. There is optional version of ReLU when we have like this type of negative part of this function. So we have two options, like this or this. The real reason to use ReLU can be like, first of all, it is still not linear, so neural network can use this part as a some point where decision threshold is happening internally, but also we don't have any points here where we need to, let me close the window, please. I mentioned backpropagation algorithm that is crucial in order to train neural network. And this backpropagation algorithm, we will take a quick glance at this algorithm now. But one important point about this algorithm, it implies taking many derivatives all the time. So for any function, we will need to take derivatives at certain points of those functions. And the problem is that for linear part of function, derivative is just an angle, caused just by an angle. But here, we should find this angle all the time. And this is why computational complexity for this activation function is much lower. This is not the only reason, but one of like top reasons. So
Is
yeah.
Is the hinge in that function always at 0, or is that moved? Because where it goes from 0 to that linear function, is it always at the origin, at the xy intersect?
Do you mean ReLU?
Yeah, the change point, it's always there.
It's always 0, 0. Yeah.
Okay, but then the slope can be different.
Yeah, it can be like horizontal or some version with some angle here. It's two types of different ReLUs, but generally they were quite similar because there's no reason to think of this angle. The thing is, we just have this point that splits function into parts and makes it nonlinear. This is actually very important property of any activation function, that it should be not linear. There is a linear option, but if we have linear function here, neuron boils down to be just a sum of values and nothing else, because there's no reason to sum things, and that's if we have just some functionality here, neural networks doesn't make any sense. We need non-linearity in each neuron here.
So the non-linearity is like the decision, kind of.
Yeah, it's something like the point where if we go a little bit further, decision is going to be closer to one thing, opposite direction another, and combining all the small steps to decision, we can form bigger one, and it's very important because otherwise.
You don't make up your mind unless you have that.
Yeah. If you take a look like deeper here, if we put all the activation functions to be linear, we get this entire neural network can be reduced to linear function. It's like a property. So in order to make it non-linear, we should add some non-linearity, and this is done by activation function. Sometimes, in rare case, we use linear thing as an output, for example, if we need just a regression, because sigmoid, it lies in between 0 and 1 and provides us with binary decision, 0 or 1. But also we can want to get regression as an output, so like continuous value. This is one of the cases. Also, sometimes there is another very important activation function you should know about that. It is softmax. It is special activation function that splits output from one neuron into many values.
Can you draw that function too?
Actually, I can share it with you, but there's no nice graphical representation because it has more than one output. Let me try to find it.
Did we talk about softmax before, guys?
Not today.
No.
Yeah,
No.
We've seen some of the other activation functions, but not softmax, I don't think.
Softmax is one of the most popular activation functions. let me find.
I don't remember in Ramonko course. Yeah, I think we didn't.
Yeah. He might not be mentioned.
Relu, yes. Sigmoid, yes, but not. I don't recall softmax.
Mm-hmm.
You can add the note there that softmax activation function primarily is used as an output activation function for multi-class classification. Let me try to find it. There should be softmax. I have a good thing about softmax for you. Let me just try to find it.
We were given some exposure to these functions, but not any exposure to how they're used or how you might decide between them.
Just a moment. I want to send a link to you, and then I'll be able to answer. This Jupyter Notebook is a good explanation about what is softmax activation function and how it can be implemented. You can copy it to your collab and see how it works, because it is launchable. For example, this allows logistic regression to classify 10 digits instead of a couple, instead of couple. No. Okay, so this is the first thing about neural networks. Combined layers of different types, also different activation functions on different layers. Another thing you can see sometimes is nonlinear graph. As you understand, this pipeline is some kind of neural network graph. But also it is possible that we can have several different convolution layers working in parallel, for example. So that we can apply different transformations to the image, and for example, feed like this, maybe. It is possible and quite wide distributed over different architectures. So this is nonlinear graph with branches, and you can try this. I will also share a corresponding example with you, but maybe in more details we'll take a look at this graph during the upcoming course about natural language processing, because for this course I have good example with this type of graph. Yeah. So what else important? Sometimes when we use, for example, Keras, one of the high-level frameworks for neural networks, you can see weird type of layers called dropout. For now, it's not easy to explain what's the reason of having it, but just the note. It allows us to avoid overfitting in one additional way. If you remember what is overfitting from Romanko course, and we will check this a little bit later. Now a little bit about evaluation, because for further example, we need also evaluation and overfitting things. Let's say we want to create new machine learning algorithm, the most simple one, and we take 1,000 examples, for example, coins or images, and take each image as a key and the result as a value. So just copy our training set, right? And if we have the picture that is already in this training set, we can just compare by key. Take this picture. Let's say we have a set of keys. We have the list of pictures and values 0 or 1 for each picture. Our training set, right? If we save this, let's say, as a Python dictionary, we can make a lookup. Like, if we have some image, we just can try to find this image among already existing. If we found the one, we know its class, right? Seems to be kind of super naive, primitive machine learning. And what's the main problem with that? It is extremely fast. It is absolutely accurate. But what's the problem? The general, yeah.
If something that's not in the data set.
Yeah, if this is an unseen example, we cannot solve our problem, because this type of model cannot generalize its knowledge for unseen examples. And this is the problem. And generally, this model is absolutely overfitted one. So this is actually a description of overfitting. Overfitting is an effect that makes model work almost perfectly, or like perfectly on training set, but for test set it doesn't work at all, or work much worse. And for neural network, usually during the training process, we have following visualization of this process. Training of neural network is a process of minimizing or optimizing of some function. Usually we call this loss function. We will see details in that notebook I prepared, but during the training process, we minimize loss function by finding better coefficients. Initially, loss function is like this, then it goes lower, 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 but this is for training set. If we continue doing this, in the future, like we can observe two situations. One, we reach some level of quality and will stay at this plateau forever, or sometimes we can even reach zero error. It is still possible. But in fact, if we reach zero or very small error here, this also means that neural network probably just memorized everything, all the example we showed, and already cannot generalize the decision. And in order to check that moment when we have our overfitting, we also use additional data set. We call it evaluation set or testing set. That allows us like not to use these items, data items during the training process, but sometimes use these examples just to estimate the quality of our predictive model. We can use this test set to check which is loss function value, or how accuracy is good or not. So let's say black line is okay, both black lines are accuracy and I want to have it bold. Sorry. This is accuracy. This is loss. Important for training set. But if we compute the same values for test set or let's say evaluation set, we'll get something different. On evaluation set, we will see something like this, because it is the difference set and optimization for it goes a little bit slower than for generators. Then we reach some plateau much earlier than for a test and a training set, but at a certain point, this becomes growing on. And at the same time, theoretically, we get okay, it's accuracy for evaluation set goes up, then we reach some plateau, and then in the future we observe some decreasing of this curve. And if we find the minimum point here, this is the point when we should stop our training process. The thing is that after this point, we just improve the level of overfitting, or
So,
better say, making it worse.
do you just do that experimentally? Do you just go until, or is there like a method of calculating that point?
Usually, people do the following trick about that. They run all the training for some period, and sometimes check this. This is called validation accuracy and validation loss. So sometimes we check also validation values, and if we observe some trend of growing of validation loss for several epochs, or reducing validation accuracy for some epochs in line, or better, altogether, it means that there is a very high probability that we already reached the point of overfitting. And usually, after each epoch of training, we save the state of the model in special file, so that somewhere at this point, we already know that here it became overfitted. We just ignore all the results of this period, take coefficients for this epoch, and think of them as about optimal.
So it is. You just purely just do it.
Yeah, and this technique called early stopping, it is like an official term. Among many solutions how to conquer overfitting, we can use like regularizations, different type of regularization, but also in Keras and TensorFlow, there is even such a option for model training that it triggers stopping of training automatically if we have 4 epochs of rising of validation loss.
And what's an epoch? I mean, it's a period of time, but like how long of a period of time? Like what's the, it's obviously a unit of some kind.
I didn't hear you well, something with Mike, could you please?
An epoch. So obviously it's some kind of unit. Like, so what exactly is an epoch? A unit of time? Or
Actually, I was expecting you to ask the question. It's a little bit about training process. Let me explain. Generally, we have training set, right? Maybe we have training set X of size 1000 and corresponding, oh, sorry. So we have X and Y. This is training examples. This is labels, because we use supervised learning, right? Generally, we can take some neural network or some other machine learning algorithm and feed entire data here to make a small step to improve coefficients omega here. For neural networks, it's coefficients or something. It is it lets us to training process itself, how it happens. Let me talk a little bit about that. Usually, training process, it is based on gradient descent thing and backpropagation thing. Backpropagation is something that wraps gradient descent inside. We will see this in our example. But if in case of 2 variables of x length 2, we can visualize our space that needs to be optimized like this. So let's say this is an optimum point. This is x1, this is x2. Somewhere here we have the best value. And we start optimizing from this point. Gradient descent allows us to take piece of data, show it to some algorithm. We see how, we know what we need to get here, ideal labels. We get real labels predicted y hat. We compare them between each other. We know the difference between them, and this difference allows us to understand in which direction we should perform steps of updating for all the coefficients for all the variable to make step closer to our goal. So this is called gradient descent, and doing this many times, we also can visualize this even for like this type of function. So gradient descent works. It understands what direction we should make step to just to reach the optimum. We have two possibilities to go through this position. Back or further. Our procedure of comparison between ideal and obtained predictions, we can see what direction we should make a step, and so that we can go closer to minimum. So this is about gradient descent. If you want, we can dig deeper to gradient descent in the future, but the main thing here, like to make it possible to go directly to optimal value within several steps, we can take all the data, predict all the data, see all the predictions, so that we have full-size y vector, full-size y hat vector, full-size comparison with them, full derivative for this point, and make step in exactly the direction we need to make a step. But the problem is that if we are talking about, for example, images, we cannot do this easily in one step, take all the data for one step, because of two reasons. First of all, images have quite big size. So this means that we cannot load all the images into memory. Sometimes it is completely impossible. For example, we have million JPEG files, 5 megabytes. 5 million megabytes is already a big problem, especially not compressed. But it is not only like memory problem. One additional thing, whether we take one example, 5 examples, million examples, the size of step will be dependent only on our learning rate. This is a special value we call the learning rate. It is alpha in general annotation. And if we take entire data set in just to make one small step, we need to compute predictions and errors for all the values just in order to make one step. If we have million things, we have to go through million predictions, million comparisons, and it is computationally expensive. Yeah, but we also cannot take just one example, because one example is a thing that doesn't characterize distribution and general statistical things about all the data set. Instead of that, usually we use the idea of mini batch. This mini batch is a slice of data. We decide what the size. For example, it can be 128 items, 50 items, maybe 500 items, or 4 items. It is much more than one, so characterizes nature of data better. But small enough mm, to make computation faster. In this case, we do not do steps directly in our direction. Instead of that, we go some kind of like this. But it works nice and works kind of quick. So we take one mini batch and its values, then another mini batch and its values, and all our data can be split. For example, we have 10 million examples, and our mini batch is, let's say, 1,000. So we will have in our data 10,000 mini batches. We take this one, go make step, this one, make step, and when we go through all the mini batches and take all the data at least one time, this means we performed an epoch.
So it's the epoch is based on the size of the data set.
Yes, it depends on size of data set and also on size of mini batch.
Okay.
So how many steps in the epoch depends on the size of mini batch and entire data set. Yeah, and picking the right size of mini batch, it's also kind of data science problem. There is special scientific background for different cases for that. For some situations, people find it intuitively, but also there are some techniques to understand which size is better. Sometimes we have restrictions because of hardware. For example, for many cases, we cannot take mini batch more than 4, for example, just because of memory of GPU, because 6 cannot fit the memory, for example. This is the reason why for deep learning, it is very important to have GPUs with memory of big size. Yeah. So it's clear about epochs.
Yep.
Yeah. Usually we see like epochs here, and validation accuracy and validation loss are computed just for epochs. But accuracy and loss on training data are computed for each step.
Yeah. So I mean, obviously this is different based on the problem, but like in general, like, so how many epochs are you running before you will reach the early stopping point? Is it?
You will see. Currently, we are switching to this example, and I will show to you. The answer is it is different, varies dependent on situation and architecture. And sometimes it is very important to find a nice way to reduce overfitting by regularization, adding dropouts, and many more other techniques, even more data.
What's the kind of order of magnitude for number?
Yeah, to make it learn further without overfitting.
Yeah. So is it 5 or 50 or 500? Like,
it can be 3, 100, and million, and depends. So let's go through this document. Do you see the screen?
No.
Yes.
You should be able.
Oh yes, I do.
So here we have several examples about how we can train a neural network to distinguish cats from dogs. just regular classification problem, but we use different architectures of neural networks, starting from the simplest and most naive one, and finally we get kind of modern architecture and check the performance of the system using it. So let's go through. Actually, I have this document opened in two tabs. One is the original one on GitHub. I will return here later because when we will be training the network here, this notebook will be hanging for some period. And to be able to continue things, we will switch back to just GitHub page, okay? Okay, so let's go. Running the document. So, oh, sorry. I did something with that. Oh. Just a moment. Oh, I need to relaunch runtime. It is been initialized. Currently, it has been launched, and yeah. So we imported Keras. Do you know anything about Keras? Have you heard?
No.
So Keras is a high-level framework written in Python. It uses internally, it uses TensorFlow to perform computations on vectors. And Keras provides simple API, simple interface to define neural network structure with everything like the size of layers, the rules layers are connected, activation functions, and many other small tunings there. So we define a neural network and train it using this framework. Also, we get some data from this resource. You can see the link. Actually, let me authenticate. This is the procedure of giving an access to my Google Drive to this notebook because the file is stored there. Let's check if file is where it should be. Currently, we took data from my personal G drive. It lies in this folder and unpacked files here. Let's see our file systems. G drive is mounted here, but so the way is on my drive, data, Keras Python, data sets, docs with cats. So you can see here something about that. Okay. So the next step is to unzip the data. And this way, we install everything that is required for unzipping. In this Python code and Jupyter Notebook is launched in special sandbox on Google server, so that we need to install all the minimum utilities to process this archive. Once the process is done, currently we unpacking training data, dogs and cats. Also, we will unpack okay, so if we refresh our folders, we see that we have train data here. And let's go further with that. Here, you can see the procedure of splitting the data into different pieces so that we have data for training, data for evaluation, and for testing. It's 3 different pieces, usually. Okay, maybe. I didn't run the. Okay. This is the tree of files what we have now. Training set, testing set, and validation set. The reason why people use different validation set and testing set is that validation is used during the training process very often. And we make many decisions on top of output of validation tests, and making these decisions on top of validation makes us like to leak knowledge about data stored in validation set into training process. So validation slightly influences what we get in result, but testing isn't used for training at all, and used just for reporting of the quality of the system. So this is statistical things here about our data sets, and then we goes down to our first simple neural network. This Keras framework, as I told, allows us to create very simple neural network, like in several lines of code. You see here, the first line is we create the object of neural network. Then we add several different layers. You know about convolutional neural networks already. And here you can see the size of convolutional we know, the quantity of neurons we use there. It is also important. Yeah, and also you see max pooling layers. We discussed them as the simplest example of convolutions. So we reduce the size of image 4 times here. Then convolution again, max pooling again, convolution again, max pooling again, convolution again. Then we make all the things flatten in one vector, just one long vector, not matrix. Then feed all the results to 512 neurons with ReLU activation, and then use sigmoid to make prediction. In more details, we can talk later, or you can learn this example easily. It works well, actually. We created the network. Then you can see this summary thing. The object model can report about itself by printing things like this. So first of all, you can see even for this small neural network, we will need to train more than 3 million omega parameters. It's important to understand that neural network is a quite heavy function. Here we prepared for training things. We select what type of gradient descent we will use with which learning rate. Learning rate says how long this step will be, how far we jump each time. And then we should prepare our data. To be fed to neural network, and actually run neural network fitting process. Now you will see how Keras shows the training process. This is an epoch. So we, for now, we plan to have just 10 epochs. It's our first launch. And what you can see here is, first of all, a couple of loss and validation for each epoch for training data and for validation data. What you should see from here is that each time we get, at least we expect to get better loss function, better accuracy, better validation loss, and better validation accuracy. Once this is done, we will be able to see corresponding graph for that. Like, it will be a nice picture. So 10 epochs isn't too much, and we can see the training result.
And what is the batch size in this case?
This. There is entire number of whole data set, items in whole data set. And there is a mini batch that we use for one iteration.
But in this specific case, what's the size of mini batch?
Let's take a look. So we split all the data into 100 elements. So it depends on the size data, and we use 100 mini batch
chunks.
Yeah. Actually,
so in this case, 100 is 100 of mini batches, and then we need.
And the size of mini batch is entire size of data set divided
by number of mini batches.
Yeah.
Okay.
So we achieved accuracy 71%. to be honest, it's not the really bad number. It's not nice, but like random system would predict 50% because it's binary classification. But here we get 71, more than 71. It means that we already have some predictive power here. But we for sure can improve that. So let's see how we can do this. And let's see what happened to our training process. So this is a couple of curves about how we trained here. So at the top, you can see accuracy, and at the bottom, validation thing. To be honest, we could use more than 10 epochs so that we could potentially see how this validation accuracy goes worse, and this validation loss goes higher. But for this document, I already tested with many options about epochs number, and found out that 10 is optimal. You can try the same process with, let's say, 20, or if you want, we can try it together later. But believe me, it will be going down here and going up here. So this is the point when we should stop because of early stopping. After that, we will have overfitting, and we will have even worse result. Yeah. The next thing that we can do about overfitting, the first idea that appears in our minds is how we can improve our system to have lower overfitting, maybe just add much more training examples, right? Having more training examples makes our system less individually trained for each item. So if we add some data examples, it seems to be nice, but the problem is that where we can get these items from. The problem is that annotated data sets are expensive because human beings should create them. And for example, in current project, we spend about $2,000 a month, make 2 people work full time on data annotating process, and this process lasts for 8 months already. So it is quite expensive to create even not really big data set. So if there is any possibility to create auto-generated data sets, it is a nice idea. And one of approaches for that is data augmentation. It's not a thing that can solve everything, but let's suppose we have 1,000 cats and 1,000 dogs, but we want to have 10 times more. So if we take each picture, and so here we have a creature, right? Some creature. If we take this picture and reflect, making like complete reflection, we get another picture, we get completely new picture. It is for sure still the cat, but we have our data set twice as large, right? Also, we can, for each image, add some transformations. Like if we do transformation like this, we still have a cat, but it is still no picture. We also can add some affine transformation, a little bit of parallelogram, a little bit of trapeze, a little bit of noise, maybe some filters with maybe Gaussian filter or something that changes image a bit, but not as much to spoil the image. Like
Spoiling it.
sorry.
What is the danger of spoiling? Like I can imagine that you could make a mistake in these, in increasing your data set this way. Like that, I could. It's not. My instinct is that it would be quite possible to make a mistake doing this.
Yeah, it is possible. For example, if we use automatic shifts, right? We can make shift not like this maybe, but like this instead. Is this a mistake? Yes. But data augmentation is a very common technique. And in Keras, for example, just take a look at this section where I put cursor to. This is image data generator. This is the thing that performs data augmentation. So it randomly generates some rotated images with some in some range, how width is shifted, height shifted, and what we can do with images at all. This is not the entire set of operations we can do for data augmentation. But even if for some images we break image and spoil it completely, generally it is still better to have much larger data set with some few mistakes there than small data set. But if we do this like in smart way and try to be in nice ranges, we can preserve data quite nice, but have data set much larger. And let's try what's happening with this augmentation. Actually, this is an example. The original picture and a result of data augmentation. You see, this is what system does automatically. All these pictures are cats and seem to be different, but they are not. Okay, let's go through training process again. The thing is that having already more training data size, larger data size, we can train further than for 10 epochs. So also we have more data, so each epoch takes longer period. And this means that our training process will last for a longer period. And if you see, I put here 100 epochs. It means that it will take maybe, so it is almost a half of minute for one epoch. So it will be trained like 15 minutes. So we won't be waiting for the result. Here we can go down, or let's better switch to GitHub and see here while training is going there. So this is the same. Then Actually, this is data augmentation. So currently you can see some spoiled results because we don't have any face of cat, right? It's maybe not the ideal thing. Okay, so this is the output of the same training process for 100 epochs. And this is output graph. As you can see, here we have already kind of noised plateau for validation loss. And here we no longer have any improvements of accuracy, right? So this is the reason why there's no any sense to continue training. But the thing is, we were training for a longer period. We took more data. But finally, our accuracy appears to be better. As you can remember, we got something 70 plus. Here we got 80 plus.
And what we improved?
Accuracy, the final predicted.
No, yeah, I mean what we improved in the model. So
We
a
just
little bit lost.
added auto-generated examples to our training set. We use
Okay.
data augmentation technique, and that's it. And also we, because of having more data, we can train for a longer period without overfitting. And this means that we can reach better value of accuracy. But this is not the final thing we can do. Also, you can take a look here, maybe one more important thing here I didn't mention. Yeah, very important thing that I didn't mention here. One additional improvement that I didn't mention is adding dropout layer. We added augmented data, but also we add this dropout. It means that for this layer, each epoch, we randomly forget 50% of outputs.
Sorry, what? Sorry?
We just forget some outputs from previous layer. Each epoch, randomly. Select 50%.
50%.
Yeah, it depends on this number. Yeah, 50% of outputs, forget them, and continue training the epoch. This, on one hand, this adds some noise to our training process. But on another hand, it reduces the ability of neural network to overtrain. We get to overfitting much later because of this. Actually, this is the kind of the way human brain avoids the overfitting. Every one of us has an experience in their lives that we thinking of something too much. We are concentrated on something, and this like makes us not able to think about anything else, and this would lead us to death if we couldn't forget things. So ability to forget is important thing for any neural network, including human brain. Yeah, these dropouts, it's very common thing that we use in neural networks. They can be larger, smaller. There is like analytical approach how to pick dropouts, but primarily they are found by experimenting and running different architectures of neural networks.
So what's the? I don't understand the idea behind it. How does it stop overfitting?
Could you please imagine that at some layer we just for this epoch reset to not to random to kind of Gaussian distributed values a half of outputs so that they are not informative anymore. So the next layer should make decision using just a half of outputs of previous layer. So there is Gaussian part of these outputs, but other parts make this distribution a little bit different according to what we learned previously. So generally, this is not Gaussian, but kind of skewed to more optimal from Gaussian with other values. And the next epoch, the set of outputs that we forget will be different. Each epoch, this is completely new randomized thing. So theory of this dropout, very well explained for now. We can dig deeper later or using like, I can find nice description on that. But like for now, it's the intuition can be like this. We should have some way to, let's say, soften sharp parts of our function, like add some kind of filter that reduces peaks and gaps and kind of smooth the non-linearity of our overall function. Here we do this by adding the noise that cannot lead us to very strict decision boundaries. Something like this. Can I explain like more accurately? Yeah.
But so the dropout is adding smoothness by subtracting in a Gaussian curve, like I don't.
Something like this. Yeah, yeah. Maybe my explanation maybe not 100% accurate, but it is close.
Sounds good.
Yeah, I think that it's really easy to understand how exactly dropout makes this work, because for that there is very nice article on archive.org. There is original article for that. We can find it together. I have already had a chance to take a look. Yeah. Dropouts work well. Never seen any good solution without them. Okay, so let's go.
Excuse me, but here we speak about neural network, not about logistic regression.
Yeah, it's completely, it is a neural network. Actually, you should consider logistic regression as a minimal neural network. But for this situation, dropouts doesn't make any sense because your output is already output layer. Dropouts, they applicable only for hidden layers. Okay. Next step is what generally data science teams do about trying to find the best solution for their data. They go to some resources that have collections of state-of-the-art models. They get 10 top solutions that can handle type of data they have. They get these solutions, test them initially out of box, then they can do something about the change, maybe architecture, maybe combine solutions or something, so that they can obtain not bad result, even without experimenting a lot. This is like their baseline of quality they can start from. Usually there's no need to come up with new convolutional neural network for image classification, because there are many nice architectures available in the market, and not only architectures, but also already trained weights for that, for this architecture, so that we can use default weights or continue training process with our specific data and get even better result. But we can talk about this a little bit later here in document. But this part is about this VGG16. It's one of the well-known, quite old, but nice architectures. Quite old, it means like maybe 2014 or something like this. So is it old or not? Big question, but yeah. But what happens in this line? We just download previously trained weights for this architecture. Why it is important to consider using pre-trained weights? Because if we just take an architecture and initialize our coefficients, even using nice type of distribution, let's say Gaussian distribution or something, we will probably get something like this. So this is our space where we need to train our. Let's make some local even problems here, like maybe something like this. And we need to get here. If we initialize our coefficients randomly or almost randomly, we can get wherever. It's just random thing. But if we take pre-trained coefficients, maybe these coefficients weren't trained for cats and dogs. Maybe they were trained for drills and hammers. But for cats and dogs and drills and hammers, we still have many low-level features that are common. We have the idea of edge, angle, maybe texture or something that can be treated in kind of similar way, so that we for sure get coefficients not for this point for our data, but maybe for this point. So the path, the route we need to go through isn't so long. If it was like here, maybe we would be training very long way here, something like this. Okay, so here we see how we download weights. Also, we see the summary of this VGG16. Let's go to web and see the structure of this as a picture. This is
So let's say it's some already predefined architecture of neural network, yeah?
Yes. So, this is not the only one available in the market. This is one of the nice, it is powerful for simple tasks, but there are a lot, much more complex and more accurate in their prediction. Yeah, this is one.
Open source.
Yeah, you can actually, as you can see, we are using it online. It is completely freely available solution, and also you can use like many implementations. You can create your own, but believe me, there are several pre-trained in very well and debugged very well. So you should use some existing implementations for trivial tasks. You should use something already nice. So this is like just an example. Sorry for Russian language and just.
So what's already done with is that the sort of the stack of layers is figured out, the sort of sizes of the numbers of neurons, that kind of thing. That's what that is what the benefit you're getting, or is it more than that? It's actually
More than that, because we already have pre-trained weights on some
Yes.
other data. They may be, these weights potentially could be trained on something alternative, not cats and dogs, but another on vehicles and aircrafts.
So the idea is that it's more efficient to move from pre-trained weights than from random numbers.
Yes, this is exactly what I was talking about. Yeah, because it is obvious that some features are common even for cats and aircrafts. Angles, maybe texture things or something. Yeah. Let's go back. So this is carrier space description of this VGGNet. This is the code that will utilize. But what is important here, we apply further fitting for weights we downloaded from internet on our cats and dogs. We do this for like 30 epochs. And finally, we get validation accuracy like this. Quite impressive, right? And the next, I forgot what I was doing here. Let me. So about this part, I didn't mean to be talking a lot, but yeah, actually, this is several experiments with different feature extraction methods here, and we finally got even better result than 90%. So the very final value is like this. Yeah. So actually, this is something that data science engineer or team should you provide with after some period of research on some data. Whether it is images or not, what they do, they try primitive trivial architecture, then they try data augmentation and some existing architectures, and they should observe what quality improvements we get from step to step, if more complex architecture doesn't perform better than a more simple one, it means that we should rid off of this idea of using like more complex and use simpler one. If it shows better result, we can use this model, but about these improvements, we should also remember about computation complexity and computation time. Sometimes we can reach relatively easily, like quality, let's say 93% of accuracy. And it is obvious that for many cases, we can continue our improvements. And after a half of year of training and improving the architecture, get maybe 96% instead of 93%. And this 3%, the price for this 3% is like long period of research and development, but also it is likely that we get larger size of neural network that consumes more memory and more computational time for prediction time. We also call this inference time. It means that in production, sometimes it is better to have a little bit lower prediction quality, but 10 times faster architecture. Because we also should understand that if our neural network can predict, give the prediction in 20 milliseconds, it can be applicable for our business. But if it works for 2000 milliseconds, it could be not applicable for our situation. Many examples of that. For example, high frequency trading, or maybe image processing in real time for video, or audio processing. If we cannot make prediction in required maybe 20 milliseconds or 10 milliseconds or 50 milliseconds, the result we get in maybe 800 milliseconds is something that isn't actual anymore. So this lag, this delay can make our model impractical. So it's always also a trade-off between computational time and prediction accuracy. Yeah. Any questions about that for now?
I didn't get one concept, this learning rate. So
yeah, learning rate is just a number, usually called alpha, and it's only the thing, you know, when we are here, for example, during the gradient descent, we can do just one thing to understand the direction. Let's say we have computed all the derivatives, all the changes we need to apply to our weights. And we know that, let's say, our system guesses that we need to jump in this direction. But the problem is, another problem is how far we should jump, how significant this weights update we should apply. In fact, it means that we used to have at one step these values, but then we will update them with some with some, well, this is like a thing that altogether delta omegas, they form vector with length of 1. So they are pretty small. To make this step some kind of nice, not too small, we need to have a corresponding coefficient that says how far we are jumping from this point to this direction. And learning rate says that we can jump this distance or maybe this distance larger
So
than half. Yeah. And
So
the
it's-
thing is, yeah, let me finish here.
Okay.
There is important thing about that. If we take too big learning rate, we quite quickly can get here, but we cannot point the target at all because we jump over. If we take too small learning rate, we usually will be going from here for many steps, and it will take much longer time to train. And this is the reason why sometimes we use not just fixed value of alpha, but we can use thing that's called learning rate decay. It's like reducing learning rate, for example, twice as much each 10 epochs. Something like this. And actually, it works nice. So many algorithms may imply that we have not fixed learning rate, but updated instead.
Mhm. Okay, so it's again parameterization to have this trade-off, yeah, between performance and some
Yeah.
kind of accuracy, yeah.
Yeah. And in fact, even like very smart teams and scientific bound groups who do this research, let's say DeepMind, Google, Amazon, and IBM, they still have to experiment with many hyperparameters just to check how it will behave in this situation. There is no such a thing like a complete recommendation set with analytical background how to pick the proper one. It is still a matter of experimenting. For sure, some intuition, some knowledge will reduce the size of this space we have to go through, but we still need to run many experiments in parallel. Moreover, having some randomized elements of this process included in our system, for example, dropouts, they add randomization, right? Initial values of coefficients add some level of randomization. And we have many situations when we have some random things as an initial state and some random things that happen inside neural network during its training process. And this means that the training process itself a little bit non-deterministic. So it is kind of the same tendency all the time. But even for this Jupyter notebook, you will see that if you run this notebook again, you will get slightly different values for accuracy and so on. And this implies that sometimes, because of some random things, some trainings can go better than others, even having completely the same architecture. So that big companies usually, when they need to train something big and expensive, they have a farm of training processes that they launch completely in parallel with the same uh, set of hyperparameters. In some sandboxes, process goes better than in others, so that they remove that go worse, then split this farm again, like twice as much, for example, and so that they also use this technique just to find the situation where training went better than for others instances, for other instances. Is it clear?
Yeah.
So, for example, if we train something big, it is maybe important to have big computational power and some frameworks that allow us to use these farms and so. So this is why it is very rare case when some company will be retraining Google BERT, for example, because it is extremely huge. It takes a long time to go even one time, but to get nice result or perfect result, we need to run this in parallel on 300 instances. And for now, when at Google they try to train something before running training process, their data scientists use special math and approaches to estimate how expensive this training process is going to be. It's computational time for expensive hardware and power consumption things. For example, this Google BERT took about $32,000 for Google to be trained, just running the process. It's not expensive in comparison to bigger neural networks. And if you want to train something big for your company, you should understand that it may be quite expensive to run this training process. So that take pre-trained models to reduce the time.
What would you mean by quite expensive? Like how much? What are you talking?
For example, I was talking about Google BERT. It's natural language processing, not image processing. But this is still neural network. They spend about $32,000 for training this model. But it isn't the most expensive neural network to be trained at Google. Sometimes it could be like 100,000 for something. It's a realistic thing. For example, could you imagine how big input they could have for this image search system when they train it? They use almost entire internet of pictures to run training process through. And it's for sure takes at least tens of thousands of dollars to run this even one time. They can afford this, but there's each time we launch thing like this, we should have a reason for that. Something can be trained maybe in 15 minutes. There are a lot of business goals that can be achieved with very few training resources, like maybe one machine for one day or 15 minutes. For example, previous year, I was preparing the machine learning predictive model for energy company. Research took some time, but training itself takes about 50 seconds. So the problem isn't the training computational power, but knowledge what we exactly need to use under the hood. Yeah, but sometimes it is also a matter of expenses like that. Okay, so any other questions about this?
No. Actually, how does using a pre-trained thing affect the cost?
Dramatically, because you can reduce training time 100 times, for example. If you take pre-trained weights and it takes 3 days for you to train this locally, without this pre-trained weights, you probably will be trained for a whole year.
Oh, wow. Okay.
Or it would require big cluster for that, something like that. Actually, each data science company tries to control these resources for training very carefully. Once I was a part of situation when we had a bug in our provisioning script, and we created big cluster on Amazon for machine learning, and we launched 2,000 instances to run our tests on. But this bug caused the situation when we reached the goal and computed everything, all these instances, instead of being killed, they stayed running. And in maybe 4 days, we had $5,000 additional expense just because of this small bug.
Now you remember.
Yeah, I remember very well. So
I'm going to need to leave class today at 6 p.m. I have a meeting with a board of directors call at 6. So.
Actually, I think that about material for lecture itself for today, it's over. But what I would recommend for you guys is to take this Jupyter notebook I've shared with you. You will need to get training data. You can run it and experiment with different values of hyperparameters there. Please try. I will hang here for some period, maybe for 30 minutes. So you can ask questions.
Okay, so you want us to play with the hyperparameters? Is that what we said?
Yeah, you can. For example, I would recommend you to change epoch numbers for the first neural network, for very first example in this document, and see how overfitting looks like. It is here. Like, so instead of using 9 epochs, please put here 25.
So do you want us to do it now? Just
yeah, you can do this now, because if you have some problems with running notebook, I'll help you with that. Also, there are a couple of interesting things about this Jupyter notebook, because what you used before was just regular Jupyter Notebook, right? But here
Yes.
you can see at least this thing. At Google Colab, you can use Google Drive, your own Google Drive, as a data storage. You can mount it, so you will need to mount it, and at some point in your Google Drive, you should have this docs vscats folder. So I will share the folder with you, and you should add this folder into your G Drive file tree.
So where's the link for this this Jupyter Notebook? How the logistics?
You can see the link in document. In that document I've shared with you, like.
Yeah, but I don't. I see softmax.
No, let me check.
I also didn't get where to get.
Yeah, I don't.
Oh, I understand why you cannot do this. The link is to GitHub. I selected this. You can, let me show you one trick about this. So this is GitHub document. You can take this link, copy this link to clipboard, right?
Mm-hmm.
Then you go to Collab. There is a GitHub menu here. Just put a link to this notebook, and it's going to be open in Google Colab.
Okay.
Then you can run it or even copy. What I recommend you to do is save copy in GitHub. This will create your own version of this document, and you will be able to edit it and run locally. It will be saved forever for you.
So it's, which one are we looking here? It's deep learning fine tuning, that one?
Yeah.
Excellent. Okay, good. That's good to know.
Yeah, you can do this whenever it is convenient for you. Okay, so let me share. No, can't find. Please try the link just after GitHub one.
Just failed to save notebook.
You should be logged in into your Google account in this browser.
Yes, I do.
You can download this notebook if you cannot save it directly from GitHub. Notebook
Save a copy. Save get copy in GitHub. I select.
Not GitHub, in Colab. Like file.
Yeah, I open it in Colab, yeah, and now I want to save it
Save
as
a
a
copy
copy.
in Drive.
Save a copy in Drive. Okay.
Yes.
And this is in Colab, do they have some enhanced debugging in comparison with regular Jupyter notebook, or it's the same?
Actually, it is almost the same thing. The only thing they did here is a little bit new style, because they need to show something additional like RAM and disk from this sandbox. Also, they added some Python libraries to be available in distribution here, because they provide different tools to access Colab. Google Drive, Google Photos. It's interesting that directly from here you can access API of any Google document.
Okay.
For example, you can work directly with Google Sheets. Here you can access cells and so on. You can get values from Google Sheets, analyze them, put them back. So you technically can create new reports in Google Sheets from here. And for that, they provided like google.collab namespace, and there are a lot of things here. If you want to analyze Google Photos, for example, you can do this from here easily.
Okay, so it's integrated with the Google services
Yeah.
APIs.
Yeah. The only problem here it is the interface is quite slow. It isn't a really fast thing.
But what, let's say, IDE, let's say your engineers use usually to debug it, yeah?
If we are talking about Python, it is primarily PyCharm or native debugger, like primarily PyCharm.
So usually, let's say they develop it with PyCharm and then already put it to the notebook, yeah, when it's...
Actually, PyCharm supports rendering notebooks, but if I do experimental things, I primarily use notebook directly, because it is easy.
I just didn't use to the debug. It's that I cannot make easily this breakpoints. So this is a...
Usually I use debugging tools when I design some libraries. But for client code usually not as complex as library code, so that I don't need like very powerful debugger. Some prints are enough for simple client code. Did you have a chance to open the link to Google Drive to that also?
Yes, I already run it.
Okay.
I just see that first epoch time was set as 30, yeah? So I'm not sure where did you show...
You mean
which line?
You can actually turn on line numbers, but I forgot how. Sorry. I cannot find it.
I think it should be in the view, maybe.
Yeah, but I don't see it.
Follow-up section, expand table of contents. Table of contents. No.
Oh, tools, editor, and show line numbers.
Tools, editors. Numbers.
But each block has an independent numbers. Starts from the
But
first.
I don't see it. Strange.
Tools.
Yeah, I did it, but where do you see the numbers now?
You know, like you can see on the screen I opened it. Let me navigate again. Do you see the screen?
Yes. I mean that you already set the settings, but now where do you see this number lines in the editor itself?
Here.
Ah, okay. So it's inside. Yes, strange. And where do you propose to change the epochs number?
Put 25 and stay at 9 in the first neural network. Let me find this.
I'm finding 30 epochs.
Yes, me too.
No, the first one is 9 epochs.
That's why it's strange. Maybe it's...
Yeah, so 30, okay.
Maybe you already changed it, yeah, on your side.
Not
Because
really.
the first epoch is 30, batch size 20.
Let me check. When we launched together with you today, it was, I guess, smaller.
I just did Control F and just to find it, and it's
Here. Do you see the 9?
Import pickle.
Yeah, like I'm just searching for pickle. I don't have pickle in there.
Me too, yeah. So it seems like there is some difference in your version and ours.
It's weird because you opened it directly from GitHub, right?
Yes.
I didn't update GitHub. Okay, I hope you'll be able to handle this despite of weird.
Epochs 100.
Sorry?
Yeah, okay.
It's strange that we even don't have this pickle library, yeah?
It should be there. Pickle is a part of standard library of Python usually.
Yeah, just if you search the thing for pickle, it doesn't show up. Just search.
Yeah.
Did you use this link?
Yeah, we don't have any other link. Just
Let's check. Maybe something. Let's.
Yeah, some standard plugins or something you have, or
No, I actually I did the same thing in the very beginning of lesson. I took this link. Actually, this is the one I opened, right? And here I got so where is it? Memory. Compile. No, oh, yes. So here's the part. I opened this one directly from GitHub. Okay, let me share it with you.
Okay, it's under data pre-processing. There are 24 hidden cells. You need to open those up and then you can find them.
There are some hidden cells.
Yeah, under the headline data pre-processing, underneath that headline is where closed files there.
I understood what happened here.
Yeah, there you go.
It hides automatically.
Yeah, and so when you search, it obviously doesn't search hidden ones. So underneath data processing is where it is. Boom.
Okay.
There we go. That was a good use of the extra time.
Tomorrow in the morning, before having a lecture, we will meet, of course, online. Hiroshi Shibata. He's a consulting person who connects Japanese business who needs some artificial intelligence bound solutions with Ukrainian implementers and consultants. So you'll be able to listen to his presentation and then you can ask questions. And I think it's going to be interesting for you to communicate with him because he's also a very business bound person. Yeah.
Very interesting. And that's at the same time, correct? Yes.
9 a.m. I guess. Actually, my discussion with him was like, I asked him what time will be the most convenient for him, and he told that maybe in the morning. So this was the answer. So maybe not from very beginning, maybe from 10 a.m., but it will be available in the morning. Okay, guys. I think that for today we are over, and let's get down to this tomorrow in the morning. Thank you.